Dear students, welcome back. So in the previous class, we had done the Fermi Dirac statistics, wherein we have seen that if you are going to increase the temperature, how does the electron move from the valence band to conduction band, or you can say from below the Fermi level to above the Fermi level, or how the electron is moving with the temperature. So as we are increasing the temperature, the priority of the transition of the electron was increasing. All right. We had also understood what is the Fermi energy, and we have seen that the conduction electron is not randomly distributed, rather they are highly quantized. So all these electrons are getting distributed according to the Pauli distribution principle, and the electron with the lowest energy will be taking up the bottom of the energy state, and the electron with the highest energy at the 0 Kelvin is called Fermi energy, right? So those electrons which will have the highest energy at 0 Kelvin, it will go to the highest energy state, and that energy of the electron is called Fermi energy. Now today we are going to calculate what is the value of the Fermi energy at 0 Kelvin. So what is the numerical value of the Fermi energy at 0 Kelvin? So naturally it should depend upon what is the total number of the electrons. So more is the number of the electrons, more will be the number of the energy states. So naturally it should be very evident that the numerical value is also going to dependent upon what is the total number of the electrons that is conduction electron that is present. So naturally we'll have to calculate what is the total number of the electrons that is present over there. To calculate the total number of the electron present there, we require to find out what is the density of the states. So to find out the Fermi energy at 0 Kelvin, we require to first understand what is the density of the states. Then we already know the Fermi Dirac statistics, right? And of course we should know what is the total number of the energy states. So using those things we have to calculate the Fermi energy at 0 Kelvin. So let us start this lecture with freshly. So first we have the density of states. So density of the state says that, let us suppose we have any material, we have any bulk material, right? This is any bulk material. In this bulk material, let us suppose we have taken a small energy range, and this small energy range that I have taken is between E and E plus D. Let us suppose one of the limit I am saying is this is your E, this is your E, and other limit that I am going to take is E plus DE. So this is the range that I have taken, E plus DE is the delta E or DE, whatever you say, is the range that I have taken. So between this range, how many number of the energy states are there? Between this, how many number of the energy states are there? That is called your energy states. Naturally, more is the number of the energy states, more will be the number of the electrons, because in each of the energy you know, we can have the two electrons according to the Pauli exclusion principle, which is also called the fermions, one with the spin up, another with the spin down, right? So that is basically called your density of states. So naturally the bulk material that we have taken is the three-dimensional material, right? So per unit volume, what is the total number of the energy states that we have in a energy range, a small energy range E plus DE, that is going to tell us about the density of states. So now let us try to see the definition clearly. What is this density of the states? The derivation part of this I'm not going to deal with because it's not in your syllabus also, right? So whatever is the mathematical expression we'll be getting, so qualitatively that expression we are going to directly use to calculate the Fermi energy. So let's look into the definition. Density of states, which we also call DOS, is essentially the number of the different states at a particular energy level that electrons are allowed to occupy. That is, number of the electron states per unit volume per unit energy is your density of states. So you should remember this definition as it is. The bulk property, and what are the some of the bulk property of the material? Bulk property that we have taken the 3D solids, right, or whatever the state it is available. So some of the bulk properties like your specific heat, the paramagnetic property or susceptibility and other transport phenomenon of the conductive solids depend on these functions. That is, on the density of the states, some of the bulk properties are determined, right? So whether the density of a state is more or density of the state is less, depending upon, you can have the specific heat, the paramagnetic susceptibility and other transport phenomenon which is essentially required for the conductivity. All right, the density of states calculation allow want to determine the general distribution of the states as a function of energy and can be determined the spacing between the energy bands in semiconductors or in the metals anywhere. Mathematically, the density of states is given by, that is GED, that is between the any two energy state, 8 root under 2 pi m to the power 3 by 2 h cube. So naturally here everything is constant. This is the mathematical that this has been derived. So what I am saying, this is your 8 root under 2 pi m to the power 3 by 2 h cube into e to the power 1 by 2, that is square root of e into dE. This is your mathematical expression for density of a state. That is how many number of the energy states are there between any two energy difference, E and E plus dE in a solid. Right. Now the solid can be taken in the different form. So what are the different form that we can take? We can take the bulk material that we have not given any shape. So just we have taken any bulk material. So this we are calling the 3D. And this formula that I have taken, e to the power 1 upon e to the power 1 upon 2 dE is your for bulk material. Now you see how does the density of a state is going to vary. As the energy is going to increase, the density of a state is also going to increase, but it is not directly proportional. It is directly proportional to square root of the energy. So this is what we are saying. This is the curve for your density of a state for your bulk material. It's same material. If it has been taken from the sheet, that is the you can say it is the 2D, right, instead of the 3D. Now we have converted to the 2D. Then density of a state, as you can see, is going to suddenly increase. Then it take a constant value. Then again it increase. So what you find, it is going to take the state value. So at one particular value of the energy, it has gone suddenly it has increased. Then for the next it is going to be constant till we have gone to the another value of the energy. Moment we have gone for the E1 to E2, suddenly it is going to increase. Then again it is going to take a step, and then again the moment we are going to the next value, because you know energy is also quantized. So moment we are going to the next one, suddenly again it is increasing. So that is in form of the seeds. But in terms of the wire, which is also known as your quantum wire, you must be knowing what is happening. As you can see, at one particular energy state, moment you have gone to one particular energy state, the density of a state suddenly shoots up. It goes to maximum, and then as we are going to move to the next one, before you are going to move to the next one, it falls to rapidly to zero value. It will come to the initial state. Right, and then again if it is going to the next energy level, again it is going to shoot up. But in case of the quantum dot, what is happening is at one particular energy, the density of the state is suddenly going to increase. Right. Anyway, here we are going to deal with only the e to the power 1 by 2. That is, we are going to take only for the bulk material. So this value we are going to use, that is GEDE equal to 8 root under 2 pi m to the power 3 by 2 h cube e to the power 1 by 2 dE. This is your number of the energy states, right, or density of the states per unit volume, right. And this we should numerically we should always remember. Now we have to use this expression to find out the total number of the electrons at the 0 Kelvin, because as I had told you in my first slide, that if you know what is the total number of the electrons, we can also find out what is the Fermi energy. So now ahead. So let us suppose the EF, that is your Fermi energy at 0 Kelvin, is being represented by EF naught. So Fermi energy we have represented EF at 0 Kelvin, we have represented by EF naught. So you must be knowing, again I just to revise your concept, what I'm saying here, we have the different energy states. So these are your energy state that we have taken. This is your Fermi energy. This is the topmost level at 0 Kelvin, of course. So this is your Fermi energy. So we are calling Fermi energy as EF naught at 0 Kelvin. Here I have represented by F naught. So it is called EF naught at 0 Kelvin. Right. So what I'm saying, at 0 Kelvin, the highest energy occupied by any electron is equal to your EF naught. Naturally, the minimum energy occupied by any of the electron is, we can take as 0. Let any dE be the number of the electrons per unit volume. So we don't know what is the total number of the electrons over here. So let us suppose per unit volume, right, between the energy difference of E and E plus dE. So any two difference we have taken, between that difference the number of the electrons is your N. So just try to understand this. Let us suppose here I have taken the energy is this your E, and next level I am going here, and I am saying this is your first one is your E, this I am saying this is your E, and then I have gone to E plus dE. So this is your E plus dE, E plus dE. These are your two energy states, right? That is the two what we have taken, a range we have taken. And I am saying, let us suppose we have the N number of the electrons within this range only, right? Now Fermi energy is somewhere here. This is your Fermi energy. This is the highest energy occupied by the electron at 0 Kelvin. So if I am going to integrate this range if I am going to increase between the E and E plus dE, right, and minimum energy, as we know, will be your 0, and maximum energy will be here, that is your EF naught. So if I am going to integrate this, I will be able to find out what is the total number of the electrons in that specimen at 0 Kelvin. So this is our purpose, and this is what we are going to look into. So now with this concept, let us proceed. Let me delete this so that you will be able to see with a clarity. So what I'm saying, let us suppose any dE is given by, so what we can say, any dE, that is the total number of the electrons, will depend upon what is the total number of the electrons that is available between E and E plus dE, will be depending upon the density of the states. So naturally this is going to be product of density of the states. It is a product of density of the state. This is nothing, this is your density of the states between E and E plus dE, and it is the product of density of the state and priority of the occupation of those energy level by the electrons, right? So if you are going to take the product of these two, we will be knowing how many electrons are there. So the product density of available states in the energy range E and E plus dE into the priority of occupation of those energy levels by the electron will be your total number of the electrons NE dE, that is the total number of the energy states. But the probability, as we know, so probability we have calculated what is the probability of moving the electrons and so on and so forth by the Fermi statistics, which we have seen in the previous class. So this is what I have written here. The probability of occupation of given energy states by electron is given by Fermi statistics, which we are calling Fe. So therefore the total number of your electrons, we can say this is your density of states into the Fermi statistics, that is the probability of finding the electrons within those ranges, right? The number of the electrons per unit volume of the material N can be evaluated by integrating the above expression. So if this expression I am going to integrate between E equal to 0 to E maximum, where E maximum is your energy posed by the electrons, that is nothing, that will be your at the Fermi level. So then we can calculate what will be your total number of the electrons available. So this is the concept that we are going to use over here. So what we can say, the total number of the electrons will be equal to N will equal to Ne. Ne is nothing sure that we have taken over here. NED, that is, this is what we are finding out. The total number of the electrons is the product of the density of the states G, D, and your Fermi statistics, that is probability of finding the electrons within that density of the states. So it is your product of the density of the state, that is your GE into Fermi Dirac statistics. So what I'm going to do, I'm just going to substitute all those values. E maximum will equal to your Fermi energy that I have already explained you, and we know at 0 Kelvin 100% of the electrons will be lying below the Fermi level. That we already know. That is what we have understood. We have, if we have the n number of the electrons, we have n number of the energy state, right? But in each of the energy state we have the 2 electrons, so all the electron is getting filled up by total n by 2 number of the electrons. So 50% of the energy state is still empty, right? This 50% is still empty, which is above this, and this is called your Fermi energy. This is called your Fermi energy, EF. So naturally this will be your maximum value of the energy at 0 Kelvin. If you are going to increase the temperature, then only the electron start moving up. But here I am going to calculate as 0 Kelvin. So n, the number of the electrons that I am seeing over here, can be given as the product of the density of, let's say, GD, the mathematical expression for which we already know, and Fermi Dirac statistic over here will be 1, because if the probability is 100%, we can say the probability is equal to your 1. So the value of Fe I have substituted is equal to 1. Alright. Now substitute the value of GD, that is the density of the states. So density of the state is equal to this one, right? This is the value of the density of the state that we have taken, and this value of the density of the state we require to substitute in the above equation. So let us see if I am going to substitute what is the value we are getting. N equal to, so here I am going to substitute this. So what I have done, just I have substituted the value, nothing else, right? GED into 1. So only GED is there, so that value I have substituted. So whatever is your constant, those things I have taken out of the integration. So what are the constant value that we are getting over here? So this entire value is your constant. So what is the variable we are going to from one energy state to another energy state? So except your energy, everything is constant. 8 is constant, 2, pi, m is the mass of the electron, h your Planck's constant. So except energy, everything your constant. So all the constant I have taken out of the integral. So all these constant I have taken out of the integral, e to power 1 by 2 d. Integrate this. So this will become e to power 3 by 2. This will be your e to power 3 by 2 divide by 3 by 2. So this I have taken with multiplication into 2 by 3. Right? Put the upper limit and lower limit. So upper limit is equal to how much? Is equal to your E max. This is E max is nothing, is equal to your Fermi energy. You see over here, E max is nothing, is equal to your Fermi energy, EF naught. So this value that I have substituted minus upper limit is anyway 0. So this is the value of the n. So number of the electrons that you are getting is equal to 8 to the 2 pi m to the power 3 by 2 upon h cube. H is your Planck's constant, 2 by 3 E F naught whole to power 3 by 2. So naturally if I have to calculate EF at 0 Kelvin, right? So what we require to know, what is the value of n, and the value of n we have got from here. So what we can say, so just I have rearranged this equation. So 8 into 2 is there. You can see here you have got the 8 and here you have got the 2. So 8 into 2 has multiplied. So this is what the 16 has come, root under 2 m to the power 3 by 2, and pi by 3 I have taken separate. So here you have the pi, right, and here you have the 3. So pi by 3 has been taken over here, EF to the power 3 by 2. So this is what this has just been rearranged. This is the value of the n that you have. All right, this I am deleting so that you will have the clarity in seeing the video. Now EF naught will equal to how much? So just you rearrange this equation, right? So all these things will come on this side, and EF naught 3 by 2 is there. So if this side it will become 2 by 3. So by taking that rearrangement, what we are saying, this value is coming out equal to h upon 8m whole to power 3 by 2 into 3n by pi. This is your Fermi energy at 0 Kelvin. This is the value of your Fermi energy at 0 Kelvin. Naturally, h is the value of the Planck's constant. 8 is the constant, m is your nothing, is your mass, right? 3 is again constant, pi is constant, right? All those things. Now let's find out what is the value of EF naught. So naturally here you have the 3 by 2. So this side it will become 2 by 3. So what is the value of EF naught? Let us see. So EF naught equal to how much? H square upon 8m 3n by pi whole to power 2 by 3. Now here you see H is your constant, 8 is again constant, m is the mass of the electron, 3 is constant, and pi is constant. So what is variable? N to the power 2 by 3. Right. So for all these things, if I'm going to substitute, that is except the value of n to the power 2 by 3 that I have taken over here, n to the power 2 by 3, and for all other things I have substituted the value, and that we are taking as a constant. So what I'm taking, this entire factor I have taken as constant, and this constant I have called as b, right? And I have substituted those value, and then value of the B will be coming out equal to 5.85 into 10 to the power minus 33 joules into n to the power 2 by 3. So this will be your Fermi energy. So Fermi energy at 0 Kelvin, that is EF naught, right, is coming out equal to how much? 5.85 into 10 to the power minus 33 n to the power 2 by 3 joules. So this is what I had told you. If you know how many electrons are there, that is here the electrons are your conduction electron, then you can find out what is the Fermi energy at 0 Kelvin. Therefore, dear friends, we have calculated Fermi energy at 0 Kelvin. Your question can also be the calculate the number of the electrons in terms of the Fermi energy, right? So at 0 Kelvin, that is also the same thing. Instead of EF, you have to calculate what is the value of N. That we have done one step ahead only, right? So that can also be the question. So in this way, we have understood how to calculate the number of the conduction electrons, or how to calculate the Fermi energy at 0 Kelvin. Now we have learned some of the outcome of your quantum theory of conductivity, and this theory we are going to apply maybe in the next class. And then whatever the failures we had seen, that is let us suppose we had a failure on the number of the conduction electron. According to the classical theory, if the number of the conduction electron is going to be more, conductivity should be more, but we say it really practically it does not satisfy. Now here again we are going to, whatever we have learned with this, we are going to apply this theory, right, on the different tenets of the conductivity, right? Whether it may be the number of the electrons, or it may be the specific heat, right, it may be the temperature. So all those things we are going to see, and whether this quantum theory is going to satisfy all those conditions or not. So this is what we will be looking up in the next class. Thank you very much.